Okay, we're going to be looking at rotational kinetic energy and solving a specific problem. And so if we look at the actual problem, we see that it is a familiar problem, one that we just recently solved. We have a mass 2 equal 5 kilograms connected to a cord going over a pulley that has radius r and mass m, where the radius is 0.1 meter, the mass is 10 kilogram. Mass 1 is connected to the other side of the pulley by the cord, and its mass is 10 kilogram. Now, after a while, the mass 1 falls from its original height to its new height, and of course, mass 2 rises. And we'll denote the original starting point of mass 1 as yi, the ending point as yf, and we'll denote h equal to yi minus yf. What is the velocity of mass m1 after falling height h? Well, conservation of energy, we are going to consider the system isolated. So the system consists of mass 1, mass 2, the mass of the pulley, and earth, and of course the cord. But we will assume the cord is massless. Our conservation of energy equation states that change in potential energy plus change in kinetic energy must equal 0. We can flesh that a little further because we got a change in potential energy from mass 1, a change in potential energy from mass 2, a change in kinetic energy of mass 1, a change in kinetic energy of mass 2, and a change in the rotational kinetic energy. And that is our new term. The rotational kinetic energy must be included in the total energy. What is the complete equation? We're going to have the potential energy of mass 1 final minus the potential energy of mass 1 initial, plus the potential energy of mass 2 final minus the potential energy of mass 2 initial, plus the kinetic energy of mass 1 final minus kinetic energy of mass 1 initial, plus the kinetic energy of mass 2 final minus the kinetic energy of mass 2 initial, plus the kinetic energy rotational final minus kinetic energy rotational initial. Now we want to put in the specific terms for each one of those terms cited above. And of course, as you see, we have that the potential energy of mass 1 final is mg m1 gyf, and initial is m1 gyi. And we have each one of the terms listed out for the change in potential energy of mass 2, the change in kinetic energy of mass 1, change in kinetic energy of mass 2, and at the end we have the change in rotational kinetic energy. Now we're going to let the initial velocity be 0. And this is simply to simplify the terms. So we wind up with minus m1gh because we were going to have yf minus yi, and that's going to be a minus h. We have m2gh plus m1vf squared plus m2 1/2 m2vf squared plus 1/2 the moment of inertia times the final angular velocity squared, where I is given by 1/2 mr squared, and we can relate the final angular velocity to the final linear velocity divided by r. Plugging all that in, we obtain everything in terms of h and final velocity squared. Now we can solve for the final velocity squared. Solving for Vf, we have that the final velocity squared is 2 times m2gh minus m1gh over m1 plus m2 plus 1/2 m. And plugging in the numbers, you can obtain the final answer.